Hello everyone, my name is Vaibhav Shikhar Singh and our project topic is Multiobjective A star. As from the quote, balancing the trade-offs to reveal a spectrum of optimal paths. We'll dive deep into it, but before the group members include me, Shivam Pandey, Divyanshu Singh and Aditya Vilasrao Bhagat. So let's start. The brief overview that we'll go through in this project is the introduction to A star, its need for the multi-objective search, that is our key area of key focus of research, the fundamentals of multi-objective optimizations, the MOA star algorithm that is at the core of it, the literature review and comparative analysis that we have done with approx 15 research papers in the same field, and the future directions and conclusion that will derive from this project. So, before diving into the its brother multi-objective A star, we'll first dive into the traditional A star algorithm and take a short recap of it. So, A star is a best first search algorithm that finds the optimal path by combining actual and heuristic cost estimates. So, it is given by the cost function Fn is equal to Gn plus Hn, where the Gn is the cost from the start node to the end node that you are at. So, basically, if we look at the example, and suppose we are at the node S and we have to go to till node 16. So, Gn would suffice to the cost of reaching from S to node 16. However, the Hn is the heuristic cost that is mentioned from reaching that node to the end node. So basically the costs that are mentioned like 14, 16, 18, these are actually the heuristic costs that are mentioned and that would be required to reach from that node to the end node, that is E. And if we look into the picture, the blue line represents the optimal path that has been found by the A star algorithm. So however, there were different certain paths, each having its different cost functions, but the optimal path is chosen based on the minimum cost function derived from each of the nodes. Next, we have before we know more about that multi-objective search, we have to know what is the importance of it in decision making or how we certainly make decisions in AI. So, what is decision making? So, decision making in AI is the system to analyze data, evaluate possible actions, and select the best option to achieve a goal. So it is crucial in areas like robotics, autonomous systems, and recommendation engines. Also, it has some applications in UAVs and traditional robots where they have to find certain paths. Its importance, if you have to talk about, then it's essential in decision making for automation, optimization, and efficiency in real world. Next, if we talk about the complexity, so AI must deal with uncertain and dynamic environments. Like a robot must have to be need not to be in a simple environment. It is usually present in a certain complex environment, so it needs to have that certain power to make certain decisions that make it more challenging than traditional programming approaches that we do. So basically, traditional programming and decision making in AI is quite different because traditional programming has a set of rules which a robot can follow, but decision making in a real environment is far much more complex. However, if we look at the overview of comparative decision making frameworks, so different frameworks that exist to guide AI decision making that are each suited for specific scenarios. Like if we talk about the various frameworks, so the various frameworks include rule-based systems, the probabilistic models, and reinforcement learning, which is like new area of research. However, in different contexts, here it refers to that there it can be applied across certain domains like healthcare, finance, and autonomous driving, etc. In the overall comparative view, if we talk about, though, we compare these frameworks that helps in selecting the most effective approach that is based on accuracy, efficiency, and the adaptability that we are going to take. So this is the overall comparative view. Next, here if we look more into the key points of decision making, so key points of decision making include the certain algorithms that we take for making decisions. So if we talk about the robotics algorithms, that are two types. So first one is the classic and then is the AI. So the classical models include the graph-based search potential feeds, which are mostly computationally expensive and are very less flexible. While AI-based approaches like machine learning, fuzzy logic, that enable real-time adaptations, heuristic algorithms like A star, D star, which have optimized paths. Then we have that bio-inspired methods like PSO, genetic algorithms, ACO that handle complex coordinations. So these are much more suited based more than the classical AI. As you can see in the picture, here is a short here is the short centralized and decentralized version that we have presented. Then, if we talk about more into the centralized versus decentralized approaches, then centralized control ensures coordination but can be a bottleneck. However, while decentralized control enhances scalability and fault control enhances fault tolerance, but may sacrifice global optimality. The choice totally depends on balancing efficiency and its responsiveness. However, if we go into there is much more applications of decision making in also in the adversarial games or the decision making in games. So we have like algorithms like Maxence that assumes individual maximizations, paranoid assumes opponents collude, while we have algorithms like BRS that are best reply search focuses on the most threatening opponents. Then we have improving AI. We improve AI by these strategic games. So if we see all these images, like the first one shows the difference between the classical and the machine learning approaches. So classical programming takes the rules and data and gives the answers, while the machine learning approaches take the data and answers to give the rules. Then we have centralized and decentralized. Like the centralized in this, we have the center node and all of the nodes are possibly explored, while the decentralized doesn't have a central node at all. And the gamifying simply depends on taking decisions and making decisions based on the facts and rules that we gather. They have certain type of algorithms based on it. So that was my part, and now I'll forward to Shivam for further explanations.
Hi everyone, welcome to this presentation. I am Shivam and I'm going to explain this decision making framework in AI robotics. So, in the real world applications of decision making models, we usually use three kind of robotics systems. So, first one is autonomous robotics, second is intelligent system, third one is the gaming AI. Autonomous is mainly used for the drone vehicles and autonomous things, which use the decentralized kind of the model to handle the real-time navigation and the task coordination. Or in intelligent system, AI optimize the manufacturing things like in factories, whatever the robots we are using, that is use the intelligent system, logistic or traffic or efficiency and safety in this field. Whatever the robotics we are using, that are the system behind working is intelligent systems. So third one is the gaming AI, or we can say game AI. The algorithm whatever we are using is min max or BRS, enhancing the game of multi-agent planning. So we will discuss further in this. So challenges and whatever the future trends in decision making, like handling the uncertainty and dynamics in uncertainty. In real world there is a lot of uncertainty scenarios come. So one of this is the fault tolerance. Fault tolerance is something like whatever the mishappening happened with the robot, so robot have to complete the task. So at least they have to complete. So that's is handled by the robot. Is called also known as the fault tolerance. Mainly, it is a key challenge that enable the robot to take a decision or make a decision under certain uncertainty. So scalability and decentralizations, as I explained you earlier, like centralization way of working, there is a one central unit which instruct everyone. So in decentralizations, there the robotics, a group of robots, they have to communicate or with each other, and system grow the number of can handle the number of complexity. This is not a fully centralized control become. This is the impartial to control anything or centralized advantage in algorithm, like in ongoing research continue to refine the decision making algorithms. In robotics, there is interest in hybrid approach, combine the machine learning and the classical planning to handle the edge case or to learn from the experience. So in integration of the learning, the future decision, whatever the work framework, we are increasingly integrate the deep learning and the reinforcement learning, like MD, markup decision process. We are using the reinforcement learning. We are using this all come under the integration of the new learning that handle the complex scenario input and improving through the experience. As I told, there is the lots of algorithms in the market right now in AI, like zero sort learning or no sort learning, few sort learning. This is all we will using for autonomous vehicles. Like as earlier I told you about the AI game, so best replay search is there. The problem with that traditional AI method, there is no optimistic, so we use one BRS. The BRS is a solution that is the strongest opponent move each turn, like in multiplayer game checkers or Chinese checkers. You guys know about this. The player who have the most strongest move, only they have to play, or other we are going to skip. You can see in this the diagram, it's clear that only our opponent is. So multi-robotics path planning. Here the challenge with the robot auto search, with the robot need to move without the crashing into the each other. So many things here used, like classical or heuristic or AI based approach it's using. So main goal is here is robot to the fast or smart or adaptable. So mostly AI it's working fine. So in Pareto, some Pareto optimality, it is a solution of Pareto optimal. If there is no other solution that improve one objective without worsening it the least one of the objective, so that is the Pareto. Is solution having a certain kind of cost factor, so that represent the cost of that. And the dominance relationship is a solution. A said the dominance B, if A is worse than the B, then objective is the strictly better than the least one. So these all are the scenarios where AI is used in the multi-objective optimization, or there is more optimization which the Divyanshu is going to tell you.
Hello, I am Divyanshu Singh. Now I'll start with MOA star. So MOA star is an advanced version of A star algorithm that finds the best path while considering multiple routes. It is widely used in robotics, navigation, gaming, and some AI based decision making. And instead of giving just one path, it provides multiple Pareto optimal solution, allowing user to choose based on priorities. In this, we just don't focus on single objective, we try to maintain multiple objectives together by balancing their trade-offs. Now, why we are using MOA star? So unlike A star, which just optimizes a single objective, that can be anything, like in a graph it can be shortest distance, MOA star considers trade-off between different objectives. Now it also get involved in multiple objectives, and which eventually helps in solving some real world problems. Example: self-driving cars, which balances speed and safety simultaneously. Logistics, minimizing cost while ensuring fast delivery. AI in gaming, finding the best balance between risk and rewards. MOA star helps in making smarter and more flexible decisions. Now, what is the working of MOA star? So first, it uses a multi-objective heuristic to guide the search process. It is a multi-objective heuristic which try to maintain all the objectives at the same time. It expands nodes by considering multiple factors instead of just one. It maintains a Pareto front which store all best trade-off solution. Example: instead of just choosing the shortest path, it finds multiple paths that balance time, cost, and energy. Now, a great example of MO star in action is: suppose you have ordered something online and we are using a drone to deliver a package. Now, MOA star finds multiple routes, allowing the system to choose based on parity, that is, urgent delivery versus energy efficiency. So, it tries to balances between both of them. Now, there are some advantages of MOA star. First, it solves real world problems useful in logistics, robotics, and AI. It provides multiple best solutions through which user can choose based on their own priorities. More intelligent decision making helps find the best balance between competitive goals, and it is also flexible and adaptable. So it can be used in different scenarios by just simply adjusting the heuristic function. Now, there are some challenges with the MOA star. First, it takes more time because we have multiple objectives as compared to the traditional A star. Second, it also requires more memories as we have to store multiple solutions instead of just one. Third, choosing the best path, user needs to analyze the Pareto optimal solutions to pick the best one. And the last one, complexity increases with more objective as we have to consider more goals at the same time, the harder is to compute solution efficiently.
Hi, my name is Aditya Bhagat, and I'm gonna actually talk about the literature review for this topic. In the literature review, we did 15 papers of literature review, and in the 15 papers, we actually categorized that paper in 3 brackets. First one is conflict-based and multi-agent. In the conflict-based and multi-agent, we managed the multi-agent objective for the conflicts of the different multi-objective A-star models, and then there is second one, which is hybrid evaluatory model. In the hybrid evaluatory model, there is A star and grid evaluatory that we combine these two models and enhance the performance of the multi-objective A star. And in the third category, there is 2 papers. In that 2 papers, we talked about utility-based and Pareto models. In the utility-based and Pareto model, it actually helps to make the decision for the optimization in the algorithm. Moving on to the next slide, there is in-depth key points to look at this paper. So as I told you previously, there is 3 categories that we divided this paper in, and in the given table we can see that there is the papers names and the category, key contribution, benefits and limitation for each of the papers. So first paper has like scalability of multiple tasks, this is the benefits. Second paper has the improved performance, and third paper has like balanced multi-objective search. Moving on to the next slide, there is comparative analysis and integration. In the comparative analysis and integration, there is all the papers that we talked about previously, which categorized in the 3 categories, and that 3 categories actually gives us the benefits of 3 key components. First one is efficiency. It helps us to make like decision making speed. And second is scalability. When we have like a large scale model or maybe multi models in the multiple environment, it helps us to actually do that. So third one is integration. In integration, there is MOA star for efficiency and conflict based hybrid utility based methods for comparative for the traditional approaches. And in the diagram that we can see, there is multi-objective optimization and Pareto optimization that actually visualize in this kind of format. Moving on to the next slide, there is future direction and the research gap. In the future direction, we can actually enhance the real-time heuristic, which actually makes the decision in a real fast way, in the timely manner, and we can improve the dynamic weights for the adjustment of adaptive optimization, and also scale the model in a large complex manner in a different environment and adjust the complexity of the models. And moving on to the future research. In the future research, we can actually design the hybrid model to integrate multiple objective techniques or maybe enhance the time to adapt to the game AI. Moving on, there is conclusions and key takeaways. In the conclusion, multi-objective search is crucial for optimizing decision making in complex game AI. MOA, which is multi-objective A star, efficiently integrate conflicts-based, hybrid, and ultimate-based approaches, and ongoing research is essential for enhancing efficiency, scalability, and adaptability. This is all the reference and the paper that we use to actually do the literature review for this topic, and thank you so much for listening.